Welcome to the micro communication course. So today we will see that a power transmission in a rectangular waveguide. Now already we have learned that a TM modes of a propagation and a TM modes of a propagation there. Then for the different mode, so what will be the power transmission there that we need to be learn here. For any waveguide, if you see that we should know that how much is the power transmitted. Again, when we transmit any power, there will be loss in a guide. So that's why we should know that what will be the power loss in that a rectangular waveguide. And that both the power transmission or a loss inside the guide that can be calculated using the pointing theorem. Now we know that a pointing theorem, and based on that we will calculate that a power transmitted inside the guide. That's why we need to know about that for a guide, if it is a perfectly terminated, in that case there is no reflection inside the particular guide there. So we consider here what will be the power there and within a particular area. That's why we're supposed to be consider that is about a closed area here. Then that closed area belongs to the field component. So we consider that A cross H complex conjugate of H here, that is to be considered with respect to given region here. So we have the component of electric field and a magnetic field. So to obtain the a power transmission here in a lossless medium, or you can say that that guide is about a lossless dielectric medium. So there are no loss is supposed to be considered ideal condition. So what will be the power transmitted through the guide? We can write in terms of a field component, electric or a magnetic field component directly here. So we will rewrite the equation of a power transmission, that is power transmitted is equal to 1 by twice of whatever the guide impedance we have for the given particular guide, and instead of a both the component we will consider here only the electric field component, that is about a square, and that area supposed to be considered for that particular region, that is about a dA here. Similarly, we will calculate in terms of a magnetic field component, that is about Zg here. Okay, so we supposed to be that is about Zg, and now power transmitted that we can type in terms of a magnetic field component Zg by 2 into your magnetic field component S square into dA here. Okay, that is in terms of electric field component, in terms of a magnetic field component we have written. Now how this field component comes here? So we should know the basic here. First, what is the guide impedance? That guide impedance is nothing but Zg is equal to the field component Ex by Hi minus Ey by Hx here. That is a guide impedance. Then this E, that E is nothing but what, it has a field component of X and Y. So that's why E will be what? E square is equal to Ex square plus Ey square. Similarly, we can write h square is equal to what? Hx square plus hy square. Now these are about the h and e values. Now from this we will calculate the power transmission for the TE mode or for a TMN mode. You just remember this E is about what we can say EX square plus EY square. Now generally this Z is nothing but what? If we see the Z equation of Z here, so Z is equal to what? It is nothing but what? A component of a transmitted component of electric field and a E trans, H trans, E trans and a H trans. That is about the ratio. So once we know that which field component is transmitted, then according to that we will get that ZG here. For example, I suppose to be consider that E trans here is nothing but what? E trans. That is nothing but what? Under root of what? EX square plus EY square. Okay. So now that we will get that E trans. Similarly, H trans is nothing but what? Okay. So I'll write here E trans is equal to under root of EX square plus EY square. Similarly, H trans is equal to what? Under root of Hx square plus under root of a Hy square. Now from this we can find out Z, the ratio of E trans by H trans here. Okay, so then we'll get the Z here. Okay, this way. Here we will get the Z. Similarly, here we have impedance for the guide. So using this expression, we will obtain the equation for this Z here. So that is that equation of a Z we are getting in terms of a medium constant, and then we can convert that expression with respect to the frequency here. So now we find out here what is your power transmission or a power transmitted for the TE mode. Suppose I consider that a TE mode here. So TE mode means what? That we say that a TMN, that M subscript and N subscript, it is to be used here for the half cycle variation along with width and along with a height here. So power transmitted, if it is a TE mode, then the average power transmitted through the rectangular guide, that will be is equal to under root of 1 minus fc by f bracket square by 2 of eta here. And we know that the region that for the field component ex square plus ey square, okay, we supposed to be consider that dx and dy, dx dy. Okay, so likewise. And here this expression 1 minus fc by f and 2 eta here, that is belongs to the zg here. So means we should know that guide impedance here is equal to eta into under root of 1 minus fc by f bracket square. That is about the z. And this zg we are getting for a t mode. So means this expression, if you see that here, under root of 1 minus fc by f bracket square by 2 eta, because earlier we have written that Zg by 2. Instead of that, we have written that expression here. Okay, that earlier 1 by twice Zg is there. Zg is here. If we put that, the eta is to this one now. So that is about a power transmitted for the T mode. Similarly, we can calculate that we can obtain a power transmitted for a TM mode. That is a power transmitted for the TM mode. So TM mode again we say that a TMMN transfers magnetic field, M and N is are the subscript for the half wave variation. So in this particular mode, so Zg is nothing but what? Eta into 1 minus Fc by F bracket square. That is cutoff frequency and your signal frequency. That is about a change. And then we rewrite the expression of a power transmission, that is P transmitted here, that is 1 by 2 eta root of 1 minus Fc by F bracket square into integrating A to B here with respect to the given area we supposed to be right here, mod of Ex square mod of Ey square into dx dy. So that is about your, in terms of electric field, that is about your power transmission. So what do you mean by eta here? This intrinsic impedance here. That intrinsic impedance is nothing but what? A ratio of mu by epsilon. So generally mu is considered for the free space mu 0 by epsilon 0. So then in that case we will get the equation that is a 377 ohm or a 125. Now this particular equation that Zg we got here, that is for wave impedance. Okay, so that is Zg we got here for the expression we are writing in terms of a wave impedance. So in general, as I told you earlier, that is a Z, that Zg we say that is about a guide impedance. In general, we say that it is about E trans, whatever the transverse component we can supposed to be considered. If we put that E trans and H trans here, so E trans is nothing but what? Under root of what? Ex square and Ey square. Okay, I'll write here. So similarly, this is nothing but what? Hx square plus Hy square. So now this particular component can be obtained from that given particular field component. So that field components are nothing but what? Ex. For example, I'm writing here. That is nothing but minus j omega mu by, we supposed to be right in terms of a that k component here. That is about, you can say, a k square here into dou hz by dou y. That is about your ex component. You can put that ex here, then ey, that is plus here j omega mu by k square dou hz by dou x. Then hx minus gamma k square dou hz by dou x, hy is equal to minus gamma that is k square dou hz by dou y. Now this one is about our expression. Now this all these four equation exey, hxhy. If you put here, okay, if you put that exey, hxhy here, for the ex we are getting this component, for the y we are getting this component. If we put that expression there, so then we will get that a term of this E trans and H trans here, and from that we'll get the expression of the Z is equal to, if you put all the things here, we'll get the expression of Z j omega mu by k square. Okay, that is about it. J omega mu by k square divided by, that is the propagation constant divided by k square. That is about our expression. So that we are getting. Okay, so there is this upper term, okay, and this denominator term. And if you further solve it, so that we will get that j omega mu by, you can say that a gamma. So gamma is nothing but what? Gamma is nothing but a j beta, because it is propagation term. So this term will be only omega mu by beta here. Then this z will be what? Omega mu by beta. Okay. So we can write there that a beta expression of a beta, that is about what? Under root of mu epsilon into, we have term 1 minus fc by f bracket square. Then if you put that beta here, then what happen here? So this omega mu by omega under root mu epsilon. So that will be cancelled. So we will get that under root of a mu by epsilon here into that as it is term. Okay, so what will be the term here? We have that that will go here 1 by under root of 1 minus fc by f bracket. This one is about a term. So this is nothing but what? A eta. So what we are written right earlier, this is about a eta here. Mu by epsilon is equal to eta. And then as it is term, we have 1 minus fc by f bracket. Okay, so this one is about our expression. So this one is for what mode? We can say we have the T mode. So similarly, we need to calculate Z for the TM mode, because Z is equal to omega mu by beta. Here we are getting for the T mode, but Z is equal to beta by omega epsilon, that we are getting for the TM mode. This is for the TM mode. This is for the TM mode. Okay, so the equation will be changed here. So what we have written earlier for the power transmitted in, for the T mode or a TM mode of a propagation here, in that case, we will get that Z in terms of a intrinsic impedance and a frequency. Then next, we will learn that what are the power losses. We'll see that power losses in rectangular waveguide. Okay, power losses in a rectangular waveguide. Now, generally, for a rectangular waveguide, there are two types of losses. One loss, if you consider here, that is a two losses. So one loss is about what we can say a dielectric loss, and another loss is about what we can say ohmic loss. Okay, so that dielectric loss means what? What dielectric medium we are supposed to be considered when your wave is propagating in a guide. So that is about a loss. And here the ohmic loss is about that in a rectangular waveguide. So internal wall of a guide are conducting one. So that's why losses in that a walls. Okay, that losses in a guide walls, waveguide walls. That is called as the ohmic loss. In general, if you see these particular losses for the guide, so we need to calculate the losses for the T mode and the losses for the TM mode. And then we should know that a general equation of a loss, that is about a low loss dielectric medium. In that case, sigma is very, very less than omega epsilon, sorry, mu epsilon. Okay, so that we supposed to be considered here. So now for this particular medium wherever we have sigma is very, very less than mu epsilon, then what will be the loss when your wave is traveling through this particular medium when we have this sigma is less than mu epsilon? So if it's supposed to be wave is propagating in a space or in particular plane, we have this medium is sigma is less than very, very less than mu epsilon. In that case, for this loss for this given particular medium is equal to what? Sigma by 2 under root of a mu by epsilon. Then mu by epsilon is nothing but a eta, that case eta sigma by 2. So that eta is nothing but what? Intrinsic impedance. And sigma is about what we say that a conductivity. That loss in a rectangular waveguide, that is nothing but what? A attenuation in a waveguide because of that dielectric medium or attenuation because of that ohmic law. So attenuation because of the given medium in a rectangular waveguide for the T mode, so we say that for the TEMN mode, in that case, loss will be for the guide. It is about a sigma, then a eta, twice of under root of 1 minus Fc by F bracket square. Here we have just write the expressions for this particular guide. So for a given particular guide, so what expressions we are getting? So this eta into 1 minus Fc, that will be for the Tm mode. So eta by this one, this term, eta by this term. So this is for the T mode. For the Tm mode, if it is a TMNN, this is for the TMMN mode. So then is equal to the term will be okay vary here. So sigma eta 2, and this term is adding 1 minus Fc by F bracket. It is multiplying here. It is a denominator because for the Tm mode of a propagation. Now we should know that at what particular frequencies, whether we say that f is greater than the fc or fc is greater than the fc, according to that we'll get the equation of the attenuation for the TE mode or a TM mode of propagation. If f is greater than the fc, okay, so we can say that if the f is greater than the fc, so we will use this equation here for the TE mode. If f is less than the fc, then we'll use the equation for the TM mode of a propagation there. And then overall power losses we supposed to be calculated. That is in terms of whatever the total loss, or we can say that a power transmitted here is equal to whatever that actual power transmitted through the guide plus what will be the power loss through the guide. Total actual input power transmitted at actual power transmitted through the guide plus whatever the power loss. And it is depending upon that what will be the loss or attenuation we say. That's why alpha g, that is about the attenuation when your wave is propagating in the z direction. And in this case, we supposed to write expression for the guide in terms of a power loss by what will be the power transmitted. Okay, what will be the power transmitted? That is about the loss as well as the guide expression that we can calculate. And in general, this we say that power transmitted and power loss. So we should know the component of electric field and magnetic field because wave is traveling so that through the guide. So it has a field component that are electric field and a magnetic field component. So in this case, we supposed to consider that a field component, if it is a electric field now, we supposed to be consider that it has a field component E0 here, and your wave is propagating. They have the loss when wave is propagating in the z direction. Similarly, for the H, we supposed to be calculate that as 0 e raised to minus alpha c that into a z here. And through that, P is equal to E cross H. So that's why we are getting the expression in which P transmitted, that is P transmitted plus P loss, whatever we have written here, that is about e raised to minus twice because we have the field component of a electric field and a magnetic field. That's why it is about a minus twice of alpha g into its area. So that the expressions we are getting. So that value generally is alpha, what we are writing here in terms of a power loss or what we can supposed to be right here. That is about the attenuation there. Okay, alpha g. That is about the attenuation. So generally attenuation takes place inside the wall of a waveguide. So means we can say that that loss is called as a surface loss, means attenuation because of that a surface resistance of a guide here. Because field are your wave is propagating through the guide through the total reflection. So here is reflecting from this wall. So some of the field components can be penetrate through these guides of the wall, and because of that, if how much is the penetration occur inside the waveguide, that is nothing but what a loss for this particular guide. So that we are getting based on that what will be the conducting wall surface. So from that we can calculate that a skin depth for this given particular conducting wall there. Means how your wave propagating inside this particular wall into this particular wall there. So that's why we should know that what is the surface resistance for this particular wall. Okay, that is about waveguide. And that surface resistance of this guide wall, it is depending upon that resistivity of this particular wall as well as the conductivity of this particular wall and how much is the penetration takes place. That's why skin depth there. So this attenuation inside that particular guide wall, it is depending upon that a surface resistance of a guide wall. So we'll see first what will be the surface resistance. So surface resistance generally is equal to what? What will be the resistivity and what will be the skin depth. So generally we say that the surface resistivity we can write in terms of a conductivity there. So that is 1 by a conductivity here and your skin depth. Rho is equal to 1 by sigma. Okay, likewise. So that's why 1 by sigma and a skin depth here. And in terms of a that surface resistance when we are writing in terms of a attenuation here, that is about what we can say that attenuation because of that skin depth, so alpha g by sigma. So that is equal to under root of pi f mu by sigma. Okay, that is about it, pi f mu by sigma. So we talk about that what will be the power loss per unit length of a guide when we consider that a field component, because we have the a surface component for the guide wall, and we supposed to be consider whether that field component, we say that is about a field vector, it is propagating here. So there will be a vertical component, there will be a tangential component. Okay, so now means normal component and tangential component. So now wave is propagating through this guide. At this point we will get the two components, one is the tangential and a normal component. So now the loss occur at this particular walls of a guide. So that's why that loss corresponding to the particular surface of this walls or a conductor there. Okay, so that we supposed to be consider a tangential component of a guide. So now which tangential component? So here we consider that for the given particular guide, how your wave is propagating. Suppose I am saying that this is about our rectangular waveguide. This one is about a rectangular waveguide. And here we supposed to be consider a direction of propagation of a guide that is its head now. This is about its head direction of the propagation of a wave. We supposed to say that one is about x, this is the view y now. And since we have the field component propagating, your wave is propagating through the guide, and in that case your total signal propagation is takes place because of that reflection here. So we supposed to be consider that plane of a propagation, that will be a yz plane. So for this yz plane we have a tangential component that will be what? Hy and a hz. Okay, that is about a tangential component. So we supposed to be find out a tangential component of a that guide. So we say that h square is equal to what? Whatever the field component of, we say, hx square plus hy square likewise. Okay, supposed to. That is about a mod here. That is about a mod. Likewise. So for that purpose, for a tangential component, so what will be your a field component? So in that case, so we supposed to be consider that htx and a hty. These are the tangential components, htx and hty. So here we will write the loss expression for the guide. It has a tangential component for a given particular surface. So that is about what we can say st here for a given particular surface twice of zz into a given particular area here. We supposed to be consider that is a dA here. This one is the expression. So sorry, this one is nothing but the expression for the whatever the attenuation. Okay, this one is the expression for the attenuation. And this particular factor, we supposed to say that this one is about a power loss. So power loss is equal to what? Rs by 2 into whatever the power loss for this given particular tangential component. So loss with respect to tangential component. That's why we'll get the attenuation here with respect to the surface. Okay, so that is about your power loss when we supposed to be consider that ohmic surface and what we can say that that loss because of that dielectric medium. Okay, so that is about a power losses in a rectangular waveguide that we have seen. Similarly, we say that for a given particular mode, we can calculate that different loss. Okay, but here the surface we consider here to calculate the loss. So that is about your power losses. Then another topic we will see here. So that is excitation. Excitations of modes in rectangular waveguide. Means what? Excitation means how we are providing the input to the guide. Based on that, we have the different modes of excitation. So means RF input supposed to be providing to the guide. How we are providing. So that's why we supposed to say that there are the excitation of a guide. Excitations for the mode. Can be a T mode or a TM mode. And as we say that T mode, we supposed to say that M and N. How many M is nothing but how many half cycle variations along with A, how many half cycle variations along with a B. They're about the two different M and N. So based on that, we say that these are about the different way of the excitations mode in a rectangular guide. So we supposed to be consider here a rectangular waveguide. And for this rectangular waveguide, I'm supposed to say a small cut section of a guide. This one is about a rectangular waveguide. Okay, I just cut here the guide here. Now, how we are exciting to this particular rectangular waveguide? So, if we excite through the coaxial cable, okay, this way, we supposed to be consider that a coaxial cable here. That is about the input, and that length will be what? A lambda by 2. So one input from the guide here is supposed to be we are providing, or one probe we are going to consider here. So that mode is nothing but what? T10 mode. We are exciting only one particular mode. Okay, one particular plane. Now, if I suppose to consider that this one is about your rectangular waveguide. Okay, this is about your rectangular waveguide, this particular patch here. And we are exciting this guide, okay, now through two different poles or two different probes here. Supposed to be considered here about your one probe we supposed to be. We are exciting through the one probe here. We are exciting through the another probe. There are the two inputs now. Now these are the two poles we are coupling. So that is mode we say that is about a T20. Okay, we are just coupling the two modes here. Okay, so that is about through this guide. Then another one is about we have a rectangular waveguide and we supposed to be exciting through the simple probe directly, not from the bottom. Okay, directly here. So that is called as a TM11 mode. This one is called as a TM11 mode. And then in the similar way here, if supposed to be we are using a two probe, this is about a direct one. Okay, so we supposed to be consider that is about a direct probe here that is to be used two poles. So you can say that TM21 means from this particular flat shape, okay, from the bottom, okay, we say that a given particular rectangular waveguide from the bottom we are just exciting one more. We are inserting, we are using a two probes that is about a T20 mode. So likewise, only one from the short circuit end if we are providing the input to the guide, so TM11 mode. If from the short circuit two probes we are inserting, we say that TM21 mode. So that is about your excitation modes. That's all about your excitation mode in a rectangular waveguide. So for any probe, when we are supposed to be exciting the waveguide, we supposed to be consider that how we are exciting the guide, and for that excitation of a guide, so what will be the difference between these two particular probes? So that two particular probes, that difference is nothing but a lambda by 4. Okay, this distance, that will be a lambda by 4. And through that, we supposed to be excite the rectangular waveguide. So we should know that what will be the length of the transmission line, and what will be the probe at what particular place we are putting the that antenna probe there, so that we'll get the excitation modes in a rectangular waveguide. That's all about excitation of a modes in a rectangular waveguide and a losses in a rectangular waveguide. Thank you all of you.